Hey, what's up, Chem peeps? Mr. Boylan in the house. What in the heck are we gonna do in this vid? We're going to explain how the solubility of a substance can be understood in terms of chemical equilibrium. Breaking it down, as always. 1. Predict the solubility of a salt, or rank the solubility of salts given the relevant KSP values. 2. Calculate the molar solubility of a salt given its KSP. 3. Calculate the KSP of a salt given the molar solubility. Alright, so let's start this vid by talking about ionic compounds and recognize that all ionic compounds dissolve in water to some degree. Those ion dipole attractions between the ions in the ionic compound and water, your dipole. However, many compounds have such low solubility in water that we classify them as insoluble. So let's first take a look at a highly soluble salt like sodium chloride. When I shake this into solution, notice that in my solution, the ionic compound completely dissolves into its ions. Highly soluble. However, we also have ionic compounds that are much less soluble. For example, strontium phosphate. Shaking some in. Boom. Notice this time, in this less soluble salt, not all of the solid completely dissolves into ions. Now, how do you know which ones are soluble and which ones are insoluble? Well, you can turn to a list of solubility rules that indicate which compounds are generally soluble and which are insoluble. Boom. This is what you use in your first year of chemistry. However, you don't get one of those handy solubility rule charts for the AP exam. You need to know these 4 ions are always going to be considered highly soluble in ionic compounds: sodium, potassium, ammonium, and nitrate. And although the solubility rules beyond those, are not required, it's a good idea to take some time and get familiar with some of these solubility rules. Now, we're talking about this idea in our unit of equilibrium. So let's talk about how the solubility of a salt relates to equilibrium. Let's come back to this slightly soluble salt, strontium phosphate. I'm again gonna shake some of this into water. Boom. The equilibrium that exists is the equilibrium between the dissolving of the solid into aqueous ions and the ions recrystallizing into the solid salt. So let me restart. I'm gonna shake in only a little bit of salt. Boom. It all completely ionizes. There's no solid. The rate of dissolution and the rate of recrystallization is not the same. It's all dissolving, no recrystallizing. We're not at equilibrium. It's not until I add enough salt, to saturate the solution that we can say we're at equilibrium. That the rate of the dissolution process and the rate of the recrystallization process are the same. Now, here's another way to look at that at sort of the macroscopic level. This time, I'm using potassium dichromate, and I start with just pure water. As I add my solute to the water, notice that at the macroscopic level, I can tell that this solution is not yet saturated, because I don't see any solid forming. I add more. It's getting more and more concentrated, but still not saturated. Adding more. Oh my goodness. Boom. I know that I've saturated the solution because I start to see the formation of a solid, and I've reached equilibrium. Doesn't matter how much more solid I add, I can't force any more of it to dissolve into solution. So when we apply equilibrium to the solubility of slightly soluble salts, we're still talking about a K value, or an equilibrium constant value. We're just specifically going to call it the solubility product constant. Now, as you think about why we call it a solubility product constant, think about this generalized equation for the dissociation of a solid ionic compound into its ions. The solubility product, or equilibrium constant expression, is still products over reactants. But because the only thing that is aqueous is our products, and our reactant is a solid, that reactant isn't going to show up in the equilibrium constant expression for the solubility product constant, KSP. Let's take a look at an example of lead 2 chloride. Think about the ratio of the ions in that solid ionic compound. When I put it into solution, it's going to dissolve to form 1 lead 2 ion and 2 chloride ions. So my KSP expression is also going to show that relationship for the stoichiometry that we see when dissolving a slightly soluble ionic salt in water. Now, what do the relative sizes of KSP tell us? The larger the KSP value suggests more dissociation to ions and greater solubility. So as I take a look at this table of solubility product constants for some common ionic salts, recognize that KSP, as any equilibrium constant, is defined as the concentration of products over the concentrations of reactants. But keep in mind, our reactants are solids and therefore don't really take part in the KSP expression. So the general expression for KSP focuses on just the concentrations of your product, your aqueous ions, raised to their coefficients in the balanced chemical equation. And the larger the value of KSP, it implies that you've got a greater number of those ions in solution. It's a more soluble salt the greater that KSP value. Conversely, a smaller KSP value suggests less dissociation to ions and less solubility. So one more time, this generalized equation for the dissociation of a slightly soluble salt into its ions. We define KSP as products over reactants, but again, our focus is only on the products because our reactant is a solid. Boom. Generalized KSP expression. Smaller a KSP implies smaller concentrations of products and therefore smaller concentrations of aqueous ions. And that brings us to the last thing we need to talk about, and that's the idea of molar solubility. It's related to KSP. Recognize that solubility is the amount of solute that will dissolve in a given amount of solution at a particular temperature. The resulting solution is said to be saturated. Again, come back to this simulation. I start with pure water. I start adding my solute, potassium dichromate. More concentrated, more concentrated, more concentrated, more concentrated, more concentrated, more concentrated, more concentrated. Oh my goodness. Boom. Saturated. And as we think about molar solubility, we want to then think about how many moles per liter of that solute can I get dissolved at a given temperature. So molar solubility, number of moles of solute that will dissolve in a liter of solution. In other words, molarity of the dissolved solute in a saturated solution. And for your generalized reaction, you can determine molar solubility using KSP, the balanced equation for the dissolution of that salt into its aqueous ions in water. Lastly, recognize that although molar solubility and KSP are related, you can only compare solubilities of compounds by comparing their KSPs when the compounds have the same dissociation stoichiometry. Again, this takes some practice, but simply recognize if you're looking at a table of slightly soluble salts, you could totally use the KSPs to compare solubilities of, say, barium fluoride and calcium fluoride, because they each dissociate into 3 ions. I could tell that the barium fluoride is more soluble than the calcium fluoride, directly from the KSP values. But I couldn't do that with, say, barium fluoride and barium sulfate. Barium fluoride dissolves into 3 ions, where barium sulfate only into 2. So you can only compare solubilities using KSPs if the salts dissociate into the same number of ions. All right, and that does it for this vid. Have a fantastic day.